Your lecturer is Dan Hooper. Dr. Hooper is a senior scientist and the head of the Theoretical Astrophysics Group at the Fermi National Accelerator Laboratory. He is also an associate professor of astronomy and astrophysics at the University of Chicago. Dr. Hooper received his PhD in physics from the University of Wisconsin-Madison. He is the author of 2 books written for non-scientists, Dark Cosmos and Nature's Blueprint. Dr. Hooper's television appearances include Through the Wormhole with Morgan Freeman and Space's Deepest Secrets, and he has been interviewed on NPR's Science Friday.
No single individual in the history of science is as well known or as iconic as Albert Einstein. And this is true for some very good reasons. Reasonable people might be able to have a debate about who is the most influential or important scientist of all time. Names like Isaac Newton or Charles Darwin come to mind. But by any reasonable measure, Albert Einstein is certainly a contender for this top spot. His insights and his ideas revolutionized the way that we think about our universe, radically transforming our understanding of space, time, gravity, light, energy, and matter. But despite his enormous importance, Einstein was only a human being. He made mistakes from time to time, and he had flaws like the rest of us. There are any number of books, lectures, and documentaries that celebrate the great scientific achievements of Albert Einstein, and rightfully so. But in these lectures, I'm not going to focus on Einstein's greatest achievements. Instead, I'm going to describe some of the most significant instances in which Einstein's reasoning or intuition led him astray. Or to put it another way, I'm going to tell you about what Einstein got wrong. In some of the cases that we'll talk about, we'll see that Einstein's flawed thinking led him to conclusions that turned out to be false. For example, he convinced himself that black holes couldn't possibly exist, although we now know that they most certainly do. Einstein was also convinced for quite some time that our universe couldn't be expanding. In this case, however, he eventually changed his mind when presented with evidence to the contrary. In other instances, Einstein's intuition or philosophical prejudices prevented him from accepting truths about our universe. Perhaps the most famous example of this was his struggle to accept the reality of the strange quantum nature of the subatomic world. And in yet other cases, Einstein led himself to pursue long and stubborn quests, which ultimately went nowhere, and in hindsight, clearly had no chance of succeeding. But before we go any further, I want to make one thing absolutely clear. These lectures should in no way whatsoever be taken as a criticism or a condemnation of Albert Einstein's scientific legacy. I consider Einstein to be an absolute giant of a scientist, and so does virtually every physicist that I've ever met. He was a genius, and he was responsible for some of the greatest breakthroughs in the history of physics. He deserves all of the credit that he's been given. But Einstein's greatness does not mean that his career was without failures. He had his share of mistakes and errors, and sometimes big ones. But even if Einstein's failures were sometimes greater than those of other scientists, this was only because his ideas and opinions were so much more bold. If you don't want to lose big from time to time, you don't bet big. Intellectually speaking, Einstein bet big, and he bet often. For a number of reasons, I think it can be both interesting and important to discuss the failures of a scientific giant like Einstein. For one thing, I think our tendency to deify great figures in history can sometimes have negative consequences. If we teach our children that our most admired heroes, whether athletes, presidents, or thinkers, never made any mistakes, this can make it difficult for them to imagine that they themselves could ever rise to such heights. And as a physicist, I personally take great comfort in the fact that there were problems that even Einstein couldn't solve, or even got flatly wrong. The fact is that even the greatest among us have made many mistakes. We've all had many failures. To deny that about someone is to deny something about the human condition itself. To really pay full tribute to Albert Einstein, I'd argue that we need to appreciate not only his great successes, but also his challenges, mistakes, and errors. But before we get into examples of what Einstein got wrong, we're going to have to set some groundwork and establish some important things that he got very right. So we're going to spend the remainder of this lecture and the entirety of the next lecture talking about what is probably his single greatest contribution to physics, the theory of relativity. But to understand just how important and revolutionary this theory was, we have to appreciate what came before it. We need to understand not only what Einstein built, but what he overthrew. Between the late 1600s and the beginning of the 20th century, the field of physics was dominated by the ideas of Isaac Newton. The Newtonian laws of motion and gravitation had up to that point in time been the most successful scientific theory in all of history. Newton's ideas, of course, were challenged from time to time during those 2 centuries, but these ideas always seemed to hold up. This is not to say that the field of physics didn't make any progress during that time. It certainly did. There were many new phenomena that were discovered and that came to be understood in the centuries that followed the Newtonian era. Take electricity and magnetism, for example. Until the 19th century, we really didn't know what electricity or magnetism were or how they worked. Isaac Newton certainly didn't have a clue. But contributions from physicists such as Michael Faraday and James Clerk Maxwell dramatically expanded our understanding of these phenomena. But in doing so, they didn't overturn anything about Newtonian physics, but instead they just supplemented it. The new theory of electromagnetism did indeed offer new insights into the nature of our world, but this new theory also fit quite nicely into the older Newtonian way of thinking about physics. Electricity and magnetism were newly understood forces, but in many respects, they were not so different from the Newtonian concept of gravity. To many physicists around the turn of the 20th century, the state of physics seemed very settled. The Newtonian worldview had been very successful and for a very long time. To most scientists, it just seemed extremely unlikely that Newtonian physics would be substantially replaced anytime soon. When someone wants to describe this state of mind as it existed at the time, they usually quote the eminent physicist Lord Kelvin, who is reported to have said, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." Although it's not actually clear that Kelvin actually ever said this, the quote does seem to capture the sentiment of the physics community at the time. For a more historically reliable quote, we can turn to the American physicist Albert Michelson, who in 1894 said that it seems probable that most of the grand underlying principles have been firmly established, and that the future truths of physical science are to be looked for in the 6th place of decimals. In other words, the big ideas had already been figured out. Only the details remained to be established. And Michelson was certainly not alone in this view. Physics seemed to be on very solid footing. Few, if any, were expecting a revolution. In 1905, however, a revolution in physics did come. And perhaps even more surprising than the revolution itself was where that revolution came from. In 1905, Albert Einstein was not working as a professor at some prestigious university. He was not famous or even well known among other physicists. He wasn't even employed as a physicist at all. Instead, he was working as a third-class technical assistant in the Swiss Patent Office. After finishing his degree in 1900, Einstein had spent 2 years unsuccessfully applying for jobs teaching math or physics. In 1902, after conceding that a teaching job wasn't in the cards, he accepted the job in the patent office. The patent office job was a good job, though. It paid well, and it seemed to give Einstein enough spare time to continue his research on the side, and to work towards finishing his PhD, which he was still pursuing at the University of Zurich. As of early 1905, however, Einstein had still not finished his doctorate, and he had published only a few papers in scientific journals, and these papers weren't particularly interesting or noteworthy. At this time, at the age of 25, the prospect for Einstein's career in physics looked very bleak. Things didn't stay this way for long, however. In 1905, Einstein wrote not 1 or 2, but 4 absolutely groundbreaking papers. Any one of these 4 papers would have made him a star within the field of physics, and would have certainly secured him a position of prominence in the history of science. As far as I'm aware, a string of so many breakthroughs of this magnitude in such a short period of time had never happened before, has never happened since. And the first of Einstein's 1905 papers, he proposed that light doesn't only behave like a wave, but that it is also made up of individual pieces, or particles. At the time, these pieces of light were called quanta, and today we call them photons. This insight started us down the road to what would become quantum mechanics. We'll talk much more about quantum mechanics in later lectures of this series. In the second of Einstein's 1905 papers, he showed that the random motion of particles in a fluid could be explained and understood if the fluid consisted of a large number of individual atoms, or molecules. Now bear in mind that at the time, atoms were only a hypothetical notion, and most physicists didn't think that atoms really existed. But Einstein's paper provided concrete empirical evidence that atoms were in fact real and tangible objects. He was even able to use these arguments to make a pretty good estimate for the size and mass of atoms. It was a huge step forward. These two papers on light quanta and then on atoms made the first half of 1905 an extremely good period of time for Albert Einstein. And as a bonus, he also managed to complete his PhD in April of that year, all while working full-time at the patent office. But as good as the first half of 1905 was, I think the second half might have even been better for Einstein. It was in those months that he completed and presented for the first time his theory of special relativity. Space and time would never be the same. By 1905, Einstein had been thinking about the ideas that would eventually lead him to special relativity for about 10 years or so. He would later recall that when he was only about 16 years old and still a high school student, he would sometimes imagine what it might look like to someone who could move alongside a beam of light as it traveled through space. You might think that if you wanted to do this, you could gradually accelerate until you were moving at the same speed as the light wave. And then, while you were moving in unison alongside the beam of light would look stationary. This is how it works for other kinds of waves. For example, in a reasonably fast boat moving at something like 50 miles per hour, you could move in unison alongside a water wave. From the boat's perspective, or in that frame of reference, the wave would look approximately stationary. If you could move quite a bit faster, about 770 miles per hour, you could keep up with and move alongside a wave of sound. In the right frame of reference, water waves and sound waves can be stationary. But what about light? Einstein had reasons to doubt that light would behave in the same way that water waves and sound waves do. When we say that sound waves move at a speed of about 770 miles per hour, what we really mean is that they move at the speed relative to the rest frame of the air that they're moving through. In other frames of reference, they can be moving at faster or slower speeds. The equations that physicists use to describe the propagation of light waves, what are known as Maxwell's equations, predict that light should move through space at a speed of about 670 million miles per hour. And more interestingly, these equations don't make any reference to any medium that the light waves propagate through. There's nothing in these equations that is analogous to the air that sound waves move through, or to the water that water waves move through. Unlike other kinds of waves, it wasn't clear that light needs any kind of medium at all in order to move through space. And this raises a critical question. Without a medium, in what frame of reference does light move at a speed of 670 million miles per hour? At the time, most physicists sidestepped this question by simply imagining that light really does move through some kind of medium, a medium that they called the luminiferous ether, or just the ether for short. Although no experiment had ever detected this ether, they argued that it must fill virtually all of space. After all, they argued, the light from a distant star could only reach us if there was a continuous path filled with ether extending all the way from the star to us. And furthermore, in order for this hypothetical ether to make sense, it had to have some rather strange properties. For one thing, astronomers had long known that the planets in our solar system weren't appreciably slowing down over time. If our solar system was filled with any kind of ordinary material, like a gas or something similar, that material would act like a form of wind resistance to the planets, inducing a drag force, causing them to gradually slow down. Whatever the ether was, it had to fill all of space, but not be felt by the objects moving through it. The ether had to be a very exotic substance indeed, and the physicists of the late 19th century clamored to be the first to detect and study it. Physicists knew that if the ether existed, there would be ways to detect it, at least indirectly. At different points in time, and at different times of the year, the Earth would be moving at different speeds relative to the rest frame of the ether. At some times, the light from a given direction would be moving along with the motion of the ether. And at these times, we would expect to measure the speed of light to be a little faster than normal. And at other times, light from the same direction would be moving against the motion of the ether. And in these cases, we should measure a speed of light that's a little slower. In experiments conducted in the 1880s, the American physicists Albert Michelson and Edward Morley were able to measure the speed of light with enough sensitivity that they should have been able to detect the variations induced by the ether. But over and over again, their experiments measured the same value for the speed of light. Light, measured at different times and from different directions, always seemed to reach their experiment moving at precisely the same speed. At the time, this was a very unexpected result, and it seemed to be incompatible with the hypothesis that light moves through some sort of medium, like an ether. Some physicists tried to save the idea of the ether by suggesting that perhaps the Earth dragged a cloud of ether along with it as it moved along its orbit. This would have the effect of making the speeds of the incoming light more uniform. But these ether-dragging scenarios also had their problems. In reality, these experiments were telling us that light did not behave like other kinds of waves. In fact, there is no such thing as a luminiferous ether. When Einstein was approaching this problem, he took as a starting point, as an axiom, if you will, the idea that light always travels through empty space at exactly the same speed. He suspected this might be true for a number of different reasons. First of all, Einstein knew that Maxwell's equations predicted a specific value for the speed of light. And in doing so, these equations don't specify any particular frame of reference. This made Einstein think that the speed of light is a universal quantity, one that is the same in all frames of reference. Furthermore, these equations don't seem to require or make any reference to the ether. Unlike other kinds of waves, light can just move through space itself. Among other things, Einstein's hunch that the speed of light was a universal constant could explain why Michelson and Morley and other experimental physicists hadn't been able to measure any variations in the speed of light. To Einstein's way of thinking, light always traveled at the same speed, and any experiment you did, regardless of the time or direction, would measure the same value for this quantity. So in some ways, Einstein's premise of a universal speed of light seemed to solve some problems. But in other ways, it seemed to be very problematic. To see why, imagine the following scenario. Picture a spaceship that's moving through space at a speed of half the speed of light. As the spaceship approaches a space station, the pilot of the spaceship, they turn on their headlights. To someone who's standing on the space station, you should ask yourself how fast the speed of the approaching light beam is. Since the spaceship is moving at half the speed of light, and the light itself is of course moving at the speed of light, the incoming light should be seen to have a speed of 1.5 times the speed of light. But this, of course, is in contradiction with Einstein's starting assumption that light always moves at the same speed. To Einstein, no one should ever measure a speed of light that's 1.5 times the speed of light, or any other speed other than exactly the speed of light. So at least at first glance, it would seem that Einstein's axiom of a universal speed of light leads to paradoxical nonsense. In thinking through this example, without even knowing it, we've made use of something that physicists call a Galilean transformation. In a Galilean transformation, velocities simply get added together. In the previous case, for example, we said that half of the speed of light plus the speed of light equals 1.5 times the speed of light. Our intuition and our experience strongly supports this kind of reasoning. It just works very well in any number of situations. In fact, this kind of reasoning is so intuitive that it can be hard to imagine that the world might work in any other way. But according to Einstein, the Galilean transformation is only accurate in those situations in which everything is moving at a speed that's much slower than the speed of light. In other situations, those in which something is moving at a speed comparable to the speed of light, the Galilean transformation breaks down and it fails. In place of the Galilean transformation, Einstein instead adopted an alternative known as a Lorentz transformation. For slow-moving objects, the Lorentz transformation is nearly identical to the ordinary Galilean transformation. For example, according to these equations, two small velocities add up together normally. 1 mile per hour plus 2 miles per hour equals 3 miles per hour. In other words, our intuition works perfectly well so long as everything in the problem is moving at a speed much slower than the speed of light. But for objects that are moving at speeds close to the speed of light, the Lorentz transformations behave very differently. For one thing, combinations of velocities never exceed the speed of light. For example, half of the speed of light plus the speed of light turns out to be equal to the speed of light, according to these equations. Using the Lorentz transformation, light always travels at the same speed, just as Einstein had adopted as its initial starting point. So on June 30th of 1905, Einstein submitted a paper entitled On the Electrodynamics of Moving Bodies to the prestigious German journal, The Annals of Physics. In this paper, he introduced the theory that we now call special relativity. In this theory, Einstein replaced the more intuitive Galilean transformations with Lorentz transformations, ensuring that light always travels at a fixed and constant speed. The word relativity is apt because according to special relativity, certain quantities, like the distance between points in space and the durations of time between events, are different to different observers. Distances in space and lengths of time don't have objectively correct values. If I ask how far apart 2 points are from each other, the correct answer to this question depends on the frame of reference that one is in when they make the measurement. And the same thing is true for measurements that involve lengths of time. Quantities such as these are indeed relative to one's frame of reference. If you're hearing about this for the first time, it almost certainly seems very strange and very counterintuitive. And it should. Relativity is very strange, and it is very counterintuitive. Special relativity describes phenomena that are not at all like those we regularly experience. Human beings are strongly hardwired to intuitively understand how objects move through space and time. This is the case because over millions of years, early humans and other hominids were more likely to survive and reproduce if they could do things like evade predators and find food. These are the kind of things that one can do better if they have a solid working conception of both space and time. As a result, natural selection gradually caused our ancestors to evolve useful instincts and intuition for both space and time. But none of our hunter-gatherer ancestors had much to gain by understanding how objects behave when they move at speeds close to the speed of light. We have very poor intuition for this kind of phenomena because it wasn't useful to our ancestors. In order for us to understand these strange and counterintuitive ideas, we can't expect to rely on our instincts. Instead, we have to train ourselves to think differently. This can be done, but it requires some work. All right, let's consider an example. Imagine that I'm holding a meter stick, and that you're moving toward me along the direction that the meter stick is pointed. As you pass by me, you measure the distance from one end to the other of my meter stick. As long as you're moving at a speed that's much slower than the speed of light, you'll measure this distance to be 1 meter, just as you'd expect. But if instead you zip by at a speed comparable to the speed of light, you'll find that your measurement yields a different and perhaps more surprising result. For example, if you're moving at 60,000 miles per second, which is about a third of the speed of light, you'll measure the length of the meter stick to be about 94 centimeters, or about 6% shorter than its length when measured at rest. If you were moving at 90% of the speed of light, it shrinks even further to about 44 centimeters. And at 99.9% of the speed of light, you'll measure the meter stick to be just under 4.5 centimeters long. In addition to space, surprising things also occur in connection to time in Einstein's theory of special relativity. Picture a mechanical alarm clock. Now imagine that you set the alarm clock to go off in 1 hour. To anyone that's either stationary or that is moving far less than the speed of light relative to the clock, they will measure that an hour passes before the alarm goes off. But to someone that is moving at a third of the speed of light, it will take 1 hour and 4 minutes for the alarm clock to go off. At 90% of the speed of light, it takes 2 hours and 18 minutes. And at 99.9% of the speed of light, this length of time, which is only 1 hour in the rest frame, gets stretched to over 22 hours, almost a full day. The most famous illustration of this kind of phenomena is an example known as the twin paradox. So picture two identical twins. One grows up to be a banker and stays on Earth for her entire life. The other grows up to be an astronaut, and she travels at a speed of 99.9% of the speed of light to a distant solar system that's located 50 light years away from us. Once arriving there, she quickly turns around and returns to Earth the same way that she came, again traveling at the same speed of 99.9% of speed of light. To those of us on Earth, the astronaut's 100 light-year round trip takes just over 100 years to complete. But time passes differently in the astronaut's moving frame of reference. As far as the astronaut's concerned, only about 4.5 years pass between the start and finish of their journey. This means that the ship's clocks all measure that 4.5 years have passed. And the astronaut only ages 4.5 years. And she only eats 4.5 years worth of food and only listens to 4.5 years of music or whatever else she does to pass the time. But on Earth, 100 years of time and history have passed. And the two twins are no longer the same age. In what was only 4.5 years to the astronaut's sister aged 100 years. In all likelihood, everyone that the astronaut knew before leaving on her journey had grown old and died before she got back home. Just take a second to consider how weird and spectacular this result really is. For all intents and purposes, the astronaut in this example has just traveled into the future, making this an example of time travel. By moving at nearly the speed of light, the astronaut slowed down the very passing of time in her frame of reference, allowing her to move rapidly into the future. The closer your speed is to the speed of light, the faster you can move through time. To something that is moving at exactly the speed of light, time ceases to make much sense at all. To such an object, all events that will ever happen simply happen simultaneously. Therefore, to a beam of light, there is no such thing as the past, present, or future. There's only a simultaneous series of events. Now let's summarize these ideas and try to put them together into context and in perspective. According to Einstein and special relativity, distances in space are contracted or shortened to observers that are in moving frames of reference. And in a similar fashion, time passes more slowly in moving frames of reference. Furthermore, the closer that one gets to the speed of light, the more pronounced these effects become. And I can't emphasize enough that these effects are not illusions, and they're not merely some kind of problem with observers mismeasuring lengths of space or durations of time. The reality is that a meter stick is only a meter long in one particular frame of reference, its rest frame. And what takes an hour, according to one observer, can be much longer or much shorter to another observer. These ideas of Einstein's radically changed our notions about both space and time. From Newton up to Einstein, physicists had been imagining a world in which lengths and durations were objective quantities that everyone would agree upon, at least given a high-quality measurement. But Einstein showed that this is not always the case. Space and time are not the simple and objective quantities they'd long been thought of as. There are some quantities that are the same to all observers, but these are the exception and not the rule. For example, observers in all frames of reference will measure the same value for the speed of light. Over the past century, physicists have carried out numerous experiments intended to test the predictions of special relativity. And over again, they find perfect agreement. When Einstein proposed this theory in 1905, it was viewed with skepticism by many of his colleagues. At best, it was seen as speculative, and at worst, it was seen as nonsense. But the repeated success of this theory eventually left no serious scientists skeptical of its validity. With the discovery of special relativity, Einstein overthrew many of physics' most long-standing notions, forcing us to reimagine our very conceptions of space and of time. In the next lecture, we'll turn our attention to Einstein's next revolutionary idea, the general theory of relativity, and to the overthrow of the Newtonian concept of gravity.